All right, so we're still talking about nuclear binding energy. Okay, and I want to show you how to calculate. We've already calculated it for carbon 12. I'm going to calculate it for another nuclide right now, another nucleus right now, and that nucleus is potassium 40. Like all potassium, it has 19 protons. That's what makes it potassium. And what we want to know about potassium 40 is what its binding energy per nucleon. Binding energy per nucleon. Remember, A is the nucleon number. It's the mass number is actually the really official title for it. It tells you how many nucleons are in the nucleus. And of course, for potassium 40, it is 40. That's what the 40 means. And again, the 19 is the atomic number. The Z, which tells you how many protons there are. So we have the atomic number here. The mass number here is 40. The atomic number is 19. And the neutron number is 21. So that Z plus N equals A. Right? That's the rule. Z plus N equals A. And we want to know the binding energy per nucleon. Remember, a nucleon is a proton or a neutron. Okay? It's a generic label for particles within the nucleus like that. And so we want to know what the binding energy per nucleon is. All right? And here's how we do that. We need to find the mass difference first. And I'll tell you between what and what. But we need to find something called delta M first. And we did this already for carbon 12. We're just doing it again for potassium 40. Now, by the way, potassium 40 is about, got the number here, about 0.0117% of all naturally occurring potassium. So that's about 1 part in 10,000. One nucleus out of every 10,000 potassium nuclei is potassium 40, and it's radioactive. So there's potassium in the walls of your house. There's potassium in the ground, and a lot of it, well, 0.0117% of it, which is still a whole lot of potassium, is radioactive. It emits gamma rays. Now, what all that means, we'll talk about. Okay, but it's an interesting example of a radioactive nucleus, which is all around us. We live in a sea of low-level radioactivity all the time, and potassium 40 is part of that. Anyway, so we're getting a little off trail here, but we need to find the binding energy per nucleon. The first part is to find the numerator, the binding energy. Okay? And the binding energy we find this way. Okay, so first we want to know what the binding energy is. It's going to be so many MeV. And here's how we do that. First thing we do is we look up, we'd be given, if you want to think of it that way, we can look up the mass of potassium 40. Okay? The mass of potassium 40 equals, and I quote, from Wikipedia no less, for this sort of thing, Wikipedia is pretty good. There's not a whole lot of controversy or difference of opinion about the mass of potassium 40. So, information is pretty good. It's 39.963998 mass units. Okay. That's one thing we need to find the binding energy. But what we want to know is the difference between that mass and the mass of all 19 protons and 21 neutrons when they're all separate from each other. So we want to find the mass of the nucleus when it's together and the mass of all its individual pieces when it's apart. So we need to find the mass of 19 protons. And that is equal to 19 times 1.007. This was given. This will be given. 1.007825 mass units. And that equals, I've got it here, 19.148675. Now the reason that we start off with, I should need to back off and say this, the reason that we start off with so many significant figures, you may be wondering about that. Why don't we just say 40? And why don't we just say 19? Because when you're talking about the differences in mass between the nucleus and all of its parts, it's a pretty small fraction of the total mass. So it only shows up down in the deeper decimal places. So keeping those decimal places all the way through is important. At the end we can cut it to 2 or 3. But that's why we started off with so many, because the real differences show up not up here in the tens or ones or even tens or tenths place, but further down. And that's why we keep so many significant figures here. So that's the mass of 19 individual protons. We do the same thing with neutrons, the mass of 21 neutrons, because that's how many neutrons there are. That's going to be equal to 21 times the mass of a neutron, which is 1.008 665 mass units. And that equals, when you multiply it out, 21.181965 mass units. So what we have to do now, because again, we're comparing the mass of the nucleus taken by itself compared to the mass of all of its parts, all of its particles taken apart. And so to find the mass of all the particles taken apart, we need to add the mass of 19 separate protons to the mass of 21 separate neutrons. And when we add those up, when we take this, two numbers, and add them, and we get the mass of all those particles separate, and that equals 40.33064 mass units. So that is the mass of the particles separated from each other. 1 second here to pull my other colors out. So, what we need to do to find the binding energy of potassium-40 is to take this number and compare it to that number. You see that they're different. The mass of potassium-40 by itself, the mass of the individual particles taken one at a time and added up. Okay. So if we subtract those two, let me see, I'm going to subtract those two. I'm going to find the difference in those two right here. So the difference, the 40.33, etc., minus 39.96, gives us this mass difference right here. It gives us 0.3 666, ooh, 3 6s, 42. And that is the change in the mass. Okay, that's how many mass units different the nucleus is from all of its parts added together. Okay, that's the difference. But now we need to find the binding energy, so we need to find the rest energy corresponding to that amount of mass. 0.36662 U times C squared. Okay. And when you do that math, you get 341 MeV. So that is the binding energy. Once we find the difference in mass, in other words, we find the difference in mass between the particle, the nucleus rather, and its constituent parts. Once we find that difference, that's delta M, we then use E equals mc squared to determine how much energy that represents, and that's the binding energy of the nucleus. That's also the amount of energy needed to put into potassium-40 to break it apart. But what we're asking for is the binding energy per nucleus. Oh, this is our 341. Now what we want is the binding energy per nucleus, Be divided by A. And that is simple. That is 341 MeV divided by 40, because we're talking about potassium 40. That's A. A equals 40. So you do that math, you end up getting binding energy per nucleon is 8.5. I just leave it at that, 8.5 MeV. That is the answer. 8.5 MeV. That's how you calculate binding energy per nucleon for a nucleus. Find the difference in the masses. Take that mass difference, delta M, convert it to an energy. That's the binding energy for the whole nucleus. Then divide it by the total number of nucleons, and that's your answer. Next up, let's see, what's next up? Dum-da-dum. Next up is going to be radioactivity. Boom.